Welcome back. So in the previous video, we reintroduced or reacquainted you with RAII, resource acquisition as initialization. We talked about how it's good practice to use the constructor to go ahead and acquire some sort of resource, and then to go ahead and free that resource as the object's being torn down in the implicitly invoked destructor. We then went through the destruction process of objects. We noted that the destructor is indeed implicitly called, but there's more to the teardown process than that. We see the implicit invocation of the destructors for the non-static data members contained within that object, and then a couple of additional steps before we completed the teardown process. We mentioned that those first two, so the actual destructor and then the destruction of the data members, was what's most relevant in our discussion of the unique pointer. So that's what we're going to focus on, or what will be noted today and in the forthcoming slide. But let's go ahead and I guess maybe I should read the title before jumping into it, but we're going to talk about applying or making some of the data structures that we've seen to date. We're going to go ahead and use these smart pointers within them and show you the updates and some of the implications of doing so. So the first, I guess, kind of more classic example we went ahead and provided when we were talking about dynamic memory within classes, some of the implications, the rule of 3, well, now it's the rule of 5, etc. We mentioned that, okay, let's go ahead and build up this vector int. And here I went ahead and converted it to a class template. It's now just named vector, and it can store any element of type T. But this was like the classic RAII approach. We said that, okay, this object's going to have 3 data members. One's going to be a pointer to an array allocated on the free store. The other is going to be the number of elements housed within that array. And then capacity was going to be the number of total elements available to us within that array. We said that a great location to go ahead and grab that resource, that dynamically allocated block of contiguous elements of type T here, would be in the constructor. And we said that it was a no-no to use calls of new within the initializer list. So the body of our constructor kind of looked like this. We said array is equal to some sort of new, in this case, array of elements of type T, and we set it to the capacity, whatever value was stored in the capacity parameter of our parameterized constructor. So that was construction we acquired in the constructor. And then to go ahead and clear this out when we were done is in the destructor, we released that resource. So we said delete array. And do you remember that kind of throughout the lifetime of this object, there was the ability to go ahead and resize, get a larger dynamically allocated array by requesting it from the free store manager, copying over the contents in the previous array into the new one, and then deallocating the previous array and updating array to point to that newly grabbed dynamically allocated object. That was in the pushback function. We talked a little bit about that, and I believe we actually implemented it together. But again, this is like hallmark RAII, grabbing the initial resource. Some changes might be made during the lifetime of the object, but by the end of it, we're able to free those resources as the object is being decommissioned. Let's go ahead and talk about some of the implications if we were to go ahead and say that instead of being just a pointer to type T, array is actually going to be a standard library unique pointer to some sort of element of type T. Now here things are going to begin to diverge a little from the RAII approach that we talked about in the previous example. The reason being is that unique pointer is going to be responsible or own the actual dynamically allocated object, and its constructor and destructor will be responsible for the acquiring and freeing of the resource, respectively. So here's how the construction process might look now. And I'm going to go ahead and just assign array a new array of T of capacity. The reason I'm taking this approach is I think this is just more straightforward, and we can assign directly to a unique pointer and address. Kind of the process here is that it will go ahead and release the previous resource, and then it will acquire the new one. In this case, it was built up with nothing, maybe the null pointer. Now at this point, it's actually pointing to some sort of dynamically allocated object. It owns it. So array is responsible for managing the dynamically allocated array associated with our vector objects. Now, what that means is that the destructor for vector does not have to do anything. It does nothing. Why? Well, remember the destruction process. What's going to happen is that when some sort of vector object of type T goes out of scope and its lifetime's over, this do nothing constructor is going to be invoked first, and it does nothing. And then the next step in the destruction process for any object is going to begin to destruct the data members that were once associated with it, which means that arrays, so the standard template library unique pointers destructor is going to be called for our array data member. And when that happens during the teardown process, the memory, the dynamic memory is going to be released. And again, what we're seeing transfer here is the release of that resource is moving away from the vector, and it's now being associated with the destructor for our standard library unique pointer. So notice kind of maybe where this is going, and the nice features of it is due to this unique ownership, the responsibilities of maintaining the dynamically allocated object have moved from our kind of pure view within vector and offloaded to the standard library's unique pointer to go ahead and perform that management for us. And again, it's kind of doing the same thing. Unique pointer is simply a wrapper around a raw pointer. When we build it up, it points to the thing. Copy semantics are disabled, so this array is the true owner of that dynamically allocated object, in this case, the resource. And it's also going, and since it is the sole owner, it is responsible for releasing that object when it goes out of scope. And when does it go out of scope? Well, when the object that owns it is torn down, so when that vector object is removed. So let's go ahead and move on here to the next data structure that I'd like to consider. First in its form as introduced within the class. The next will be to go ahead and implement it using smart pointers. Okay, so let's consider a singly linked list. We had in our original definition, 2 data members and maybe some additional ones for size. I believe we might not have shown that in the video, but we definitely had you manage size for the doubly linked list assignment. But let's just look at what we got here. So head's a pointer to a node of type T, tail's a pointer to a node of type T. Now the first question here is, what owns the sequence? What owns the list portion of this object, this sequence of dynamically allocated objects chained together in memory? Well, the question, I mean, it's you. If you think about this, once you get to this point here, you could kind of begin the destruction process, or you're going to have to begin the destruction process through the head pointer. So maybe, I don't know, maybe head's kind of the owner of this sequence of nodes within memory. But anyhow, let's consider the destruction process. What we had to do before was we kind of initialized something like this. We had head, and we said something like, okay, while head next was equal to head's next. We went ahead and deallocated. We moved head to the subsequent node, and we moved next forward to the next one. Because again, once we deallocate head, we wouldn't be able to access head's next. So we're preserving the address stored here within this pointer here. So we continue this process of moving head forward, followed by next forward, and we keep doing this until head's equal to the null pointer, right? So, okay, next. So now we've deallocated that one, we deallocate that one. So head becomes next. We move next forward. We perform the deallocation, move head forward, move next forward, perform the deallocation, head forward. At this point, we'd hit that conditional, which is while head, and well, head's now 0. It's the null pointer. So we've destructed our list. Notice how involved kind of this destruction process is, and where it would have been defined was in our destructor. So just kind of looking through this, we can see that, okay, well, how we're building it up, it's going to be an elaborate, maybe not elaborate, but it will be through the different behaviors afforded to us through the public interface of our singly linked list type. It looks like the default constructor here creates the empty list where the head and tail both pull from the null pointer, and this goes ahead and it's built up through the interface since then. Notice here that, within our kind of definition of a node, all we have is one way. It's a one-way street. We can only move to the next node within the sequence. And there's no ability to kind of have this bi-directional movement through the data members afforded to us by our node struct. Okay, well, this was how it was before. And again, it's, what owned the list? There was no concept of ownership here, and that's what's going to be introduced with our unique pointer version. So here's head, which is now going to be of type standard library unique pointer, and it's going to store a node. It's going to be responsible for a dynamically allocated node on the free store, which means that head owns this node. When head goes out of scope, that node is going to get destroyed. And when does head go out of scope? Well, when the instance of singly linked list in which it is contained is at the end of its lifetime. Okay, well, how does the destruction process begin? Remember, with these smart pointers, we're not going to need to explicitly define a destruction process to clear out, to terminate or clear the end of the linked list to avoid memory leaks at the end of an object of this type's lifetime. Instead, we're going to rely on the unique pointer to go ahead and not only acquire the resource for us, but again, on the way out, to go ahead and release the resource to avoid any sort of memory leak. Well, if we look at our node pointer, that's been updated too, to kind of continue this chain of ownership. We said that the next data member is going to be, also a unique pointer. So here's what we're kind of setting up at this point. Head owns the node with the integer value of 7. That node has a next pointer, which is of type unique pointer, which means that due to this, 7 can be said to own the node storing the data 11 in it. Likewise, since that object has a unique next pointer, we can say that it owns the subsequent node within the sequence. So it owns the node with 12, and we continue this process on due to the unique pointers. You can see here that, okay, node with 11, by definition, its next is a unique pointer. So it owns the next item in the sequence, continuing this through. Okay, 8 also has a unique pointer because it's just a node object, so it owns the node with 9. And well, of course, 9 is the last element within our linked list. So it owns, well, nothing, but it owns the null pointer, which is nothing. Okay, so how does the destruction process begin? Well, remember, we've kind of cleared this out. So let me write that here. This is like cleared out, empty. You could say empty definition to maybe signify that. Because all of the memory, all of the freeing of the nodes is now going to be responsible of these unique pointers. So here's what happens. Singly linked list goes out of scope. So we have a singly linked list object. It has 7, 11, 12, 8, 9. It goes out of scope. Okay, we hit the do nothing destructor. Okay, nothing happens. Now we invoke the destructor for the head data member. What that means is this object is now getting broken down. We call the do nothing node destructor, and then we begin deallocating memory, or calling the destructor of the non-static data members owned by node. So in this case, we're going to call the next destructor, which is going to be responsible for this deallocation. So we kind of begin the process, and well, guess what? There's another next pointer, which is going to have its destructor called. So we move here, and then we continue this process. And then at one point, we get to the point where, okay, there's nothing, to be freed. So now we pick up where we left off in destructing the object. So this one eventually gets destructed. This one gets destructed. This one gets destructed. That one gets destructed, as does this one. And at the end of this operation, the destruction process of the unique pointer has successfully freed each node within our linked list sequence. Okay, so the doubly linked list. Well, actually, before we get to that, let's go ahead and just point this out here. Notice that tail is going to be a pointer, a raw pointer to a node of type T. The reason for this is that we've set up the ownership. We know that kind of heads are entry point into the sequence of ownership of each node within the sequence. So any sort of acquiring or freeing of resources is going to be governed through the entryway into the linked list. Tail is simply providing access. Just like you can own various things and allow your friends to, interact with them, here we can go ahead and take the address to one of these nodes within our sequence. In fact, the unique pointer, if we ask it for, it will even give us the address of the thing to which it's a holder for. So the cool thing here is we can begin kind of blending the raw pointers along with the smart pointers. And again, the whole point of smart pointers is to automatically manage the ownership of some sort of resource, in this case, a dynamically allocated object, specifically a node object. So the unique pointer will allow us to not worry about, okay, well, who's going to delete this if we have multiple pointers to some sort of object? Well, at the end of the day, the unique pointer is going to be responsible for that. But, until it's destructed, we can go ahead and take additional pointers, point it to things that the unique pointer owns, because we're not disrupting the concept of ownership. We're just making another way of accessing that element. And again, the key with smart pointers is to recognize that it's not to necessarily prevent access. What it's there for is to acknowledge ownership in terms of the acquiring and freeing of the resource, so that we don't have to worry about calling delete on some sort of pointer. We know that in this case, the dynamically allocated objects will expire at the appropriate time, which is during the destruction of this linked list. And you can begin to think, well, how might I do an insertion procedure? How can I link things up, etc.? How can I go ahead and, absorb a new element within our list? Well, the process is always, when it comes to linked lists, going to begin at the head. And how things are going to get inserted is, well, obviously, once you've found the location where the thing's going to go, you're going to have a new unique pointer being created, which will eventually move its resource to some pointers next, which is also a unique pointer, hence the move. And there'll be a choreography similar to what we've noticed before to successfully absorb into the singly linked list some sort of new node object. So the doubly linked list is, we've talked about this before. This is the old-fashioned way with the raw pointers, both head and tail into our linked list. We've gone through this, and I hope after reviewing the singly linked list, you're kind of familiar with the destruction operation that would occur here. How we wrote it, I believe, when we introduced this, was we start at the head and followed an identical procedure to that of the singly linked list. I mean, we could have done, we could have started at the tail and moved the other way, because remember, the difference between our doubly linked list and singly linked list is the bidirectional nature of doubly linked list, in that its nodes contain not only a pointer to the next element in the sequence, but also a pointer to the previous node in the sequence, hence the doubly linked nature of the underlying list. So how would we go ahead and put smart pointers into the mix? Well, we could start this kind of concept of ownership at either end. And what we're going to implement is going to be almost identical to what we had done with the singly linked list. But I do want to point out there are two options. You could begin this chain of ownership from the head to the tail, as we were required to do with our singly linked list, because again, we could only move in one direction. However, the doubly linked list affords this bidirectional movement, which would have allowed us to begin the ownership chain at the end of the linked list and move through the previous pointers all the way to the front. But to keep things simple, just as we did in the destructor process for objects of this type, where we essentially mimicked that of our singly linked list, we're going to begin or do the same with the smart version of our doubly linked list. So head is going to be a unique pointer to some sort of node. So head is going to own, in this case, the node with 5. Now notice how we've updated our node definition. We do a different color here. Our node definition was updated to have next be a unique pointer. So here we can see that each node is going to own the subsequent node in the list, not the previous one, because think about it. If we had 2 unique pointers pointing to one another, let's go ahead and do this. I think this will make it clear. In this case, who owns this object, assuming those were all unique pointers? Because the unique pointers implying exclusive ownership. And if both next and prev were pointing to the same object, well, that ownership isn't exclusive anymore, and they both kind of own the object being pointed to. And that violates, this whole concept of unique ownership. So in our implementation, we're only going to have a unique pointer being that of being the next field within our node objects. So we can, just as we did before for the singly linked list, head owns the node storing the integer value of 5. In turn, the node storing the integer value of 5 owns that which stores the integer object of 7, which in turn owns that which stores the integer object of 11, which in turn owns, well, nothing. But we can go ahead and write it out. But that's the ownership chain here. Starting from the head, we can see that there's a clear chain of ownership from the head all the way to the last node within the sequence. Now here's our raw pointers, which are simply there to provide us that additional access. They're not responsible for the acquiring or the deallocation of the memory associated with the nodes. Again, that is the responsibility of these unique pointer objects. And again, it's this, someone owns it, but we can go ahead and access it and interact with it through, say, a raw pointer. So tail just points to the last element. We said that was cool. And then also all of our previous pointers are also raw pointers, which allows us the functionality that we expect of a doubly linked list, and that we can move both forward through our unique pointers or in the reverse direction through the raw pre-pointers. Okay, so we'll go ahead and finish up this lesson with a brief consideration of our binary search tree. So let's go ahead and revisit the implementation we did, not but a couple weeks ago. We said that within our binary search tree, I believe we only maintained one data member, which was a pointer to the root. The root of the tree was that special object who kind of started it all. It did not have a parent, which made it unique within our tree structure. However, it did potentially have between 0, 1, and 2 children to reflect the tree's underlying binary nature. So there was the binary search tree property, which the behaviors that we implemented respected. We're not going to get into the behaviors here. We're just kind of interested in the ownership. But before we get into our smart implementation of this, let's go ahead and revisit our binary tree node here, which we had a pointer back to the parent. So here we can see that pointer. We'll maybe not draw it over that, but yeah, 5 pointed back to 6, just like 6 pointed to 5. So there was a way to go back to revisit a node's parent. And also the root node, if you recall, did not have a parent. So the root was pointing to, its parent was pointing to the null pointer. But anyhow, we, just going through this, we see that, okay, this node object has a pointer to the parent, then it has a pointer to the left node, then to the right. And then there's a couple of additional non-pointer data members, data, which was of type T1, and then some sort of key value, which we discussed in detail when we introduced our binary search trees of type T2. And if you recall kind of the destruction process, we implemented our destructor for binary search tree. Okay, and if you remember how we defined our destructor for our binary search tree, it was a post-order traversal. So we essentially go all the way down to the left until we couldn't go anymore. Then we'd go ahead and go as far right as we could. And then we'd go ahead, delete the node that we were visiting. We'd go up, go visit the right subtree before coming up and deleting the parent, and then continuing this process to perform the deletion of the nodes in the sense that we always preserve the kind of parent of the subtree that we were deleting so that we had the ability to go ahead and get from the left subtree to the right subtree. Because remember, if we deleted the root first, we've just blown out our ability to go left or to go right. So again, we had to step left and then stepped right. And then the last node that would be when the node would actually have its resource removed or freed would be after we've blown out both the left subtree as well as the right subtree. At that point, it was safe to go ahead and deallocate the memory associated with the node. Okay. So what's the smart pointer implementation look like for this? We'll go ahead and say that the root is now going to be a unique pointer, meaning that the root is going to own this node. Okay, and what's going to be important here is that that node is going to own both its left and right children. So here's the parent, here's the children, child. You can say in this case, the parent owns both node 5 and node 7. And this process continues. So 5 is then going to own the node with 2, as it's going to own the other node with the key value of 5. Okay, well, 2 and 5, these two both don't own anything. So let's go ahead and look at the right subtree of the root. In this case, we see 7, which is going to own the node with 8. And again, 8 is a leaf, so it is going to own nothing. So in this point, we can see kind of how the structure is set up, right? So when we create a binary search tree, these unique pointers are going to manage the resources comprising the tree structure. When our binary search tree object goes out of scope, so we won't need to have a definition of the destructor as we did within our example using raw trees. Instead, the unique pointers of the tree and of the nodes are going to be responsible for the freeing of each of the nodes within the tree. So we go ahead and begin this process. The binary search tree has an empty destructor now. So as an object of that type goes out of scope, the next thing is, after doing the empty destructor, begin invoking the destructor on the data member. So in this case, root. And then we get into this whole process of deallocating, say, the root node, which, well, it owns 2 unique pointers. And eventually what's going to happen is that node's going to get removed, assuming it's going in order in terms of the pointer declaration. So left gets removed, right gets removed, that node gets removed, this node gets removed, that node gets removed, and that node is also removed. At that point, the unique pointers have successfully freed the resources or the nodes comprising our tree's underlying constructor. And they're doing so on their own without our need to go ahead and implement some sort of elaborate destruction process that would go ahead and perform this for us.